Okay, my name is Ragesh Chellaton. I'm a PhD student in Professor Jules' group. I would like to thank everyone for attending this session. The theme of the current session is opening new paths with additive manufacturing, and it will be focused around 3D and 4D printing techniques. We go to our first speaker. Our first speaker is Professor Jinsong Leng. Professor Leng is director of the Center for Smart Materials and Structure at the Harbin Institute of Technology in China. His research interests include shape memory and electro-active polymers, 4D printing, sensors, and actuators. He's a member of Academia Europaea, member of European Academy of Science and Arts, fellow of ICCM and AAAS. Today, he is going to share his research experience in shape memory polymer composites and 4D printing for aerospace and biomedical applications. Let's welcome Professor Leng.
Good afternoon, ladies and gentlemen. My name is Jinsong Leng from Harbin Institute of Technology, China. So very nice to see all of you. Firstly, I would like to thank Professor Gilles to organize this workshop on future composite. Today, I'm going to talk about Shimmer Polymer composite and the 4D printing for aerospace and biomedical applications. So my talk will include 5 parts. The first, look at the background. So for Shimmer polymer, if you have orange shape like this one, when you're heating above 2 TG, above the transition temperature, the material can become very soft like elastomer. So that means you can apply force to forcing the polymer to any shape is you like. When you're cooling down below to the TG, the material can keep the shape, which means energy can store. So whenever you need, you just simply heating above to the TG. Then the material can recover to original shape, which is this one. So you have original shape, you have pre-deformed, which is temporary shape, and you have recovery shape, like this one. So for mechanism, for Shimmer polymer, normally including fixed phase and reverse phase. For fixed shape, that can retain the permanent shape, and the reversible phase, that means they can reduce the stiffness in response to different stimulus. For typical structure of a polymer network, that will including physical cross-link network and chemical cross-link network. Shimmer polymer have some advantage, like low density, biodegradability, low cost, and easy processing. But the main challenge is how to actuate, and also the low mechanical properties, including low recovery speed and low recovery stress. The solution is make a composite. To make a composite, you can including the different filler to make a different composite that have different actuation method. And also you can improve the mechanical properties, including the recovery speed and recovery strength. So like this one, the tube, this is before the deploy, and this is after the heating, then this one can deploy. So in HIT, in our institute, we started this research about 10 years ago. So, and also some colleagues do this one, around the world, including Georgia Tech, including Air Force Research Lab, and also some colleagues in Germany, GKSS. I don't want to mention everybody, but to thank their contributions. So for our work, we start to make the polystyrene, then the epoxy, shim memory, and the BMI, and the polyimide. So if you have polymer like this one, shim memory, you can do different things. So you can make a composite, and also you can make a form. The form can change in shape by heating at a different temperature. Also, you can do electric spinning to make a membrane. With this one, with a different temperature, they can remember 5 shapes, like the 160 degree, 135, 110, 90, and 65. So I take one example is polyimide-based Shimmer polymer. This one is with high transition temperature and optically transparent. So for this one, the reason we make this one is polyimide is very important substrate of optoelectrical devices. So like this one, we heating 20 seconds, this one can deploy. And with this one, I take the movie, you can see in the future, the mobile phone can changing the shape by different actuators. So if we have shim memory polymer substrate, this make an active morphing mobile phone. We also made some prototype for the OLED, but this OLED is can change in shape. We call active morphing OLED. OLED. It's also based on polyimide. You can see different temperature can changing different shape with the polyimide-based OLED. And this one is more recently we done work for deployable Shimmer Polymer solar cell. So you can see they have a solar cell based, you have Shimmer polyimide, so combined together, and then you can see this Shimmer Polymer solar cell can deploy, can open, and also you can get the current intensity, and also after 50 bending cycle, you still can see current intensity, means this one is still working. So for Shimmer Polymer composite, you can do two things. One thing is do actuations. Because you have a different composite, you can do electricity, mechanism, light, active, and microwave driving as well. And also you can do some novel features like mechanical enhancement and two-way shim memory effect and microstructure turning. So for actuations, as mentioned, you simply can move some conductivity network with the different conductive particle like nickel, carbon black, carbon nanotube fiber, nanopapers, and also the nanotube sponge. All of this, when during the heating, you have a conductivity network, then you can driving, because you can heating this one above to transition temperature, then the material can change in the shape. Then you can also do microwave, mechanism, and light, and the solutions. So I take one example. This is we make carbon nanotube sponge. The reason we make the sponge is that this one is very good conductivity in 3 dimensions. So we combine the carbon nanotube sponge with Shimmer Polymer epoxy and make a composite. Then this one have a very good conductivity. We also can make this one is a two-way Shimmer Polymer composite. So that means this one can do the bidirection actuation and the local motions. So light is very important actuation method. So we embedded the optic fiber inside optic Shimmer polymer. Then you can simply apply light in 3 to 4 micrometer wavelengths. Then you can see Shimmer polymer wire can deploy. So we also try microwave. The reason is microwave can absorb by Shimmer Polymer, by nanotube, and also this one can do the faster heating and wireless control and remote control. So you can see from 2 seconds to 30 seconds, you can see the sample can deploy by microwave with different percentage of carbon nanotube inside Shimmer Polymer. So solution is also another method. That is because physical swelling effect. You can see the wire inside polyene. You can see the after 60 minutes, this one can changing the shape. And also not changing shape, also changing the dimensions. That means in the future, this one maybe can use for the drug delivery. So this is another one. We make some humidity sensitive polymer. That means we can make some the reversible humidity sensitive clothing. You can see when this feeling warm, the flap can open, then when you're feeling cold, the flap can close. So that's based on the water-induced nothing, Shimmer polymer. So we also can do two-way by light. Very important is the PAP. That is light responsive source for converting light energy to the emitting energy. So we put this one in Shimmer polymer. So to make a composite, when you put the light, you can see this one can open and this one also can close to make a two-way Shimmer polymer effect. So we also try to do some called selective stimulus. So when we call selective, that means you can see the sample black, white, black. So when you apply the magnetic field heating, you can see only the first part deploy, but the two another part remaining to original shape. But when you apply the radio frequency, you can see the bottom one deploy, but another two parts remain original shape. Finally, when you apply the heating, you can do the middle one, which is this one deploy. So that means in the future, the stimulus can selective to driving the sample to changing the shape as you want. Like this one, it's only this part change, other two parts no shape changing. But when you apply the other stimulus, other part of the sample can change the shape. So because as I mentioned, we also can do some mechanical enhancement and also two-way shim memory effect by different the particles. This is one example. We make using some Kickstick carbon nanotube like this one, and we embed this one in Shimmer polymer, so you can see this one can improve the mechanical properties, including flexible stress, and also this one can deploy when you apply the heating source. We also embedded some nano rubber. The reason we're using nano rubber is the nano rubber also can improve the toughness, but also not cause of the thermal and the shape memory properties. So this is another example for the micro cracking. The Shimmer polymer, we can make some firm with some cracking, but when you're heating, the cracking can disappear. So you can see contact angle, that is original shape, and that is deformed to keep the shape with the low temperature below to the TG, and after heating above to transition temperature, you see the contact angle will change to original one. With this one, you can simply control the weightabilities. So this is another example. We make some grating. This is the form by Shimmer polymer. After the printing, we printing the gratings. When you apply the heating, the grating can disappear. So with this one, because the light can come in from here without grating, and with grating, the light come to this. Grating can do the beam splitters. The beam can split by gratings. So that means you can adjust the optical performance of the Shimmer polymer film. So now we're talking about some applications. The first one is the aerospace. You can see the traditionally deployable structure is this one. By complex structures, including the explosive bolt, that means a high shocking impact up to 10,000 G. But with shimmer memory, you can easy to deploy this in the initial shape, this one, and this one can keep the shape with the low temperature, but heating above to TG, this one can deploy to original shape. And very important is almost no impact. And also after you take off the electricity, take off the heating source, the material can become very hard because the stiffness of the polymer can change. The Young's modulus can change. So this one can become to a beer loading structures below to the TG. So we've done a lot of tests, especially the environmental test, including the gamma ray radiations, UV radiation, AO radiation, thermal cycling, and with a different temperature for the epoxy, center ester, and polyimide Shimmer polymers. So I take one example, that is epoxy-based Shimmer polymers. So after there are certain dose gamma radiations, you can see after certain bending cycles, the recovery ratio, which is very important for the Shimmer polymer, still can keep more than 97%. So I'll quickly go through the mechanics model. So we firstly established the thermal-mechanical counting model based on the glass and the rubber phase, like this one. So then we go into the particle reinforced Shimmer polymer by using the Multifunctional method and the Maxwell equations. So then we go into the Modulus Prediction of the unidirections carbon fiber reinforced Shimmer polymer composite. Then we can see the post-buckling. The post-buckling is very important. You can see they have fiber, they have post-buckling. So what we have done is we can predict the natural surface, curvature, and the half wavelength with this theory. And then finally, we done some work with the stress analysis of the composite Shimmer memory. That is because very important for the applications, we need the stress prediction model. So this is a very early work more than 10 years ago. You see 29 published paper. You can see the Shimmer polymer here can deploy. With this one, you can deploy solar cell panel, like this one. And most recently, we done some work. This is a solar cell panel, two panel with the hinge. When you're heating, the hinge can deploy and take off the temperature, the hinge can keep the shape. This one is also actually launched more than 4 years ago, 2017. This is another example is a truss. You can see the truss can also deploy simply by Shimmer polymer plate like this one. From 0 second to 80 second, 100 second, you can see the truss can deploy. This is more recently our work, like this one design. You have a few plates, and with this kind of design, when you're heating, this one can deploy simultaneously. Then you can see the truss can deploy. So this one was published in Composite Structures. And see details. For flexible solar cell, that is very important in the future. But how to deploy? So we patented this one actually in China more than 5 years ago, I guess. We put Shimmer polymer with the flexible solar cell form together with this one. Below to the TG, the material can keep the shape. You cannot open it. And after you're heating the Shimmer polymer above to transition temperature, this one can deploy. And the take off the temperature is can keep the shape because the modulus can change more than 200 times, like this one. So in 2016, we have chance to do the orbit experiment. This is the geostationary orbit experiment. This is a movie, and this is the orbit image after 13 days and 8 months after launching. You can see this one deployed in the space. And this is another one we call the Shimmer lenticular tube, but this one you can see can deploy by heating like this movie. And inside we can put some flexible solar cell. Unfortunately, last year, this one we have a chance, it's a payload to deploy in space. You can see this is the image base, that's 0 second, 12 second, 25, and 60 second. And this is the two Shimmer Polymer tube. Middle is flexible solar cell, which can deploy by Shimmer Polymer tube. We also make this one, this deploy hinge. You can see the hinge, you can deploy one by one. This we also call serve form. If you have camera, you can serve photo. Well, you can serve photo the solar cell and the solar cell panel as well. So this one also can make the locking and the release devices like this one, the locking status and the release status. So when you have small satellite, the qubit satellite like this one, you have release devices here. When this one open, this solar cell panel can deploy by spring. So 4D printing. So what means 4D? Everybody know this one, I guess. 3D means complex structures. Manufacturing 4D means time dependence. Means the structure can changing the shape. So by Shimmer Polymer by smart materials, that is one of the methods. So you have different methods to make the 4D printing, including FDM, SLA, flip, and the direct writings. So we make some filament by Shimmer polymers. That means after fabrications, the structure can change the shape because of memory by electricity, by magneto, or by thermal. So this is the processing. You can see this one can changing the shape by thermal and also electrical and magneto. So this one you also can see this is natural sturdy bird nest. You can see they changing the shape. So this is another we call origami structures. Combined with the traditional origami, this one can changing shape by 4D printing. So we also made some grabber memory by direct writing. You can see this one. After direct writing, this grabber can changing the shape to group some screw. So with Shimmer Polymer, you can also make sensors. So this because shape changing, and then you can simply monitor the resistance change, because the shape changing can cause the resistance change. So with this one, you can do liquid sensors. We also recently done some work with DLP for 4D printing Shimmer memory capture devices. We make some Shimmer Polymer epoxy composite with the ink reinforced with the short carbon fiber, then make a 2-dimension reinforcement. And then you can see this one can group object. So biomedical is another application. That is really work. And 4 years ago, our student makes some stent by printing PLA SMP because we have a iron particle inside. So this one can driving by magnetic field. So this is another design with the negative Poisson ratio. You can see the stent can changing the shape because the negative Poisson ratios can provide good mechanical properties and also personal customizations. So we also done some work with the tricho dent. That is based on Shimmer Polymer, but also you can see this glass sponge inspired structures. This one is also actuated by magnetic field. So look at this one. If you have a problem with bone, we have to using the bone stent. Sorry, this is in Chinese. But normally you have to do big structures and put it here. But with the Shimmer Polymer, we can firstly do personalized printing, and we also make a smaller size of the structures put inside. Then you can do remote control by magnetic field. And very important is this one is biocompatible and biodegradable. So in the future, in maybe 6-7 months or 1 year, this one can degrade it if you need it, if you demand it. So this one is the occluders. So occluder is very important. If you have problem with your heart, you normally have to put the occluder, but it's the metal-based devices, which means after Q, your heart Q, the occluder cannot take off from the heart because it's metal. But with Shimmer Polymer, it's very good. We can do the personal design and also the driving by magnetic field or by waters. And very important is after 1 year or 2 years, the devices can become to biodegradable. That means the hard problem is secured, you don't need the devices. So this is another design, but basically said we can do the 4D printing metal materials. That one can adjust the programmable and reconfigurable structures like this one. You can see the movie, we can stretch, then by heating, you can keep the shape. Whenever you need, then you're heating, this one can recover from the shape. Because this one have negative Poisson ratio, so means the structure, means the mechanical properties can adjust it, program and reconfigure it. In the futures, I think that the Shimmer Polymer is very important, one of the promising smart materials. You can see the publication number keep growth. And this more recently, we have review articles, if you're interested to have a look. So in the futures, I think smart materials can change the shape from nano level to macro level. And the reinforcement, you can have different ones. You can have particle, you can have fiber, you can form. And the application, you can do the aerospace, you can do robotic and the biomedicines. You can see the movie, BMW Gina and the morphing aircraft and the transformer. So like this one, this is Chinese passenger C919. So in the future, if we do the trailing edge and the leading edge morphing, they can reduce 8 to 12% of fuel consumptions. And also you can see the Gina, they like to have a morphing car. In the futures, we can using maybe Shimmer Polymer can do this one instead of the motor or other mechanical devices. So I like to make an acknowledgement to my colleague in Harbin and also my colleague around the world. I don't have to mention everybody, but you can see my familiar face. So I take this one as a closing. There is nothing permanent as a change. Here is tools. So I think in the future, shape changing is become promising. Thank you very much for your attention.
Thank you. Thank you, Professor Leng, for the interesting presentation. We have a couple of questions. The first question was, does shape fixity change after multiple cycle of application?
Yes, thank you for the question. Yeah. Actually, for Shimmer polymers, after the multiple cycles, for the shape recovery ratio, it does change because we done the highest after 30 cycles, for 50 cycles, even after the gamma radiations, this change, but the recovery ratios can keep more than 97%. That was published. And the shape fixed is also done similar. A little bit change, no big change, but it depends the property of your Shimmer polymers. That is first question.
And the second question is, how long does the shape changing last? Does it change with time based on the polymer life?
Yes, normally this is the based on the polymer life. This is because this is actually is polymer. This depends. Different polymer have different properties, and also, but for composite it's different. So because of if you reinforce using composites, especially using long fiber like a carbon fiber or glass fiber or Kevlar, the recovery ratio and the fixed it change, especially recovery ratio change. Normally after maybe 20 cycles, you can see the crack and you can see damage. That is because the post sparkling, because the fiber between the fiber and the polymer and the interface, they will have some damage.
Okay. Thank you, Professor Leng. Thank you for your kind answers.